and welcome to the 5th chapter of our Geotechnical Engineering course. So in this chapter, we will be discussing compaction. Specifically, we'll be defining what compaction is and we'll be discussing its fundamentals. Also, we'll go back to some moisture density relationships we have discussed in the 2nd chapter of our course. And then we'll also discuss about the standard Proctor test and the modified Proctor test, determine the factors affecting compaction, some compaction equipments, the properties and structure of compacted soils, and then the specifications, the field control, and the measurement of in situ density, and the CBR test or the California bearing ratio test. So the last two topics along with the example problems will be provided in the next video. So compaction is defined as the densification of the soil by the removal of air, which requires mechanical energy. So when we compact soils, we aim to increase their density by the process of removing air. So in the field, this requires some compaction equipment such as rollers and plate compactors. So why do we have to compact soils? So first is to increase the strength characteristics of soils. When we increase these strength characteristics of soils, we increase the bearing capacity of the foundations constructed over them. And second is to decrease the amount of undesirable settlement in the soil. So another one is to increase the stability of slopes of embankments. So the degree of compaction of a soil is measured in terms of its dry unit weight. So you will notice that prior to the compaction of soil in the field, water is sprayed in the soil. So this is because water acts as a softening agent in the soil particles. So if there is a softening agent, the soil particles can slip over each other and then they can move into a densely packed position. So the dry unit weight after compaction will increase as the moisture content increases. But beyond a certain moisture content, called the optimum moisture content, any increase in the moisture content will reduce the dry unit weight. So this is because water will now occupy the spaces that would have been occupied by the solid particles. So for you to be able to visualize it properly, I have included the compaction curve. So in the left side, we have the moisture content in percent. So in this side. And then on the right side, we have the dry unit weight in pounds per cubic feet. So the moisture content is plotted in the x-axis and then the dry unit weight for the y-axis. And then you will notice that at 9.9%, the dry unit weight is 101.1. And so it will increase at 10.6. The dry unit weight is 102.2. And then similarly for 12.1, 13.8, and 15.1% of moisture content. So the dry unit weight is increasing. But when the moisture content is equal to 17.4, the dry unit weight decreased. So because in 15.1, the dry unit weight is 107.1, and when the moisture content is 17.4, the dry unit weight is 105.8, and then it will continue to decrease. So in the 19.4 and 21.2, the dry unit weight decreased. So in this figure, we can determine the optimum moisture content, which is 15.1%. So this is the moisture content that will give the maximum dry unit weight of the soil. And in the because the moisture contents, which are 17.4, 19.4, and 21.2, are higher than the optimum moisture content, but their dry density is lower than the maximum dry density. Again, this is because the water occupies the void spaces that would have been occupied by the solid particles. So let us also go back to some moisture density relationships. So just a recap, the moisture content is the mass of water all over the mass of soils, or it can also be in the weight of water all over the weight of soil. And then the density, which is the mass of soil all over the total volume. Similarly for the unit weight, which is the weight of soil over its total volume. So the dry density is the mass of solids all over the total volume of soil. Or you can also determine the dry density by dividing the density to 1 plus the moisture content. And we have also the zero air void unit weight. So for a given moisture content, the theoretical maximum dry unit weight is obtained when no air is in the void spaces. So when no air is in the void spaces, the degree of saturation is 100%. Hence, the maximum dry unit weight at a given moisture content with zero air voids is given by this equation, wherein G sub S is the specific gravity of the soil solids, the gamma sub W is the unit weight of water, all over 1 plus the moisture content times the specific gravity of soil solids. So, gamma ZAV is the zero air void unit weight. So now let's proceed to the standard Proctor test. So the standard Proctor test is used in defining the maximum dry unit weight and the optimum moisture content of the soil in the laboratory. So it is under the ASTM designation D698 and AASHTO test designation P99. So the mold, we have this one, is attached to a base plate at the bottom. So this is the base plate, the mold, and we have this upper part as the extension. So the soil samples will be mixed with varying amounts of water and then will be compacted to 3 equal layers. So we have the hammer here, which has a weight or a mass of 2.5 kilograms, and it will deliver 25 blows to each layers. So at a drop of 30.5 mm. So after each test, you have to calculate the unit weight, then the dry unit weight, and the optimum moisture content. And then next is you have to plot the compaction curve we have discussed earlier. So that is the process of the standard Proctor test. And in this figure, the dimensions of the device for the standard Proctor test is shown. So this is the base plate, this is our mold, and then we have the extension at the top. And on the right hand side, we have the dimensions of the hammer. Also, we have the modified Proctor test. So, they created the modified Proctor test so that the field conditions, such as when the soil is compacted by heavy equipments or rollers, um, the modified Proctor test can, what is that term? We can show or so the field conditions can be kumbaga mas magagaya niya yung field conditions when the modified Proctor test, because the modified Proctor test has a heavier hammer, and then more layers of soil are compacted. So this test is under the ASTM test designation D1557 and AASHTO T180. So in the standard Proctor test, the soil is compacted in 3 layers, but in the modified Proctor test, the soil is compacted in 5 layers. And comparing the mass of the hammer, the mass of the hammer in the modified Proctor test is greater than the mass of the hammer in the standard Proctor test. And also, the drop of the hammer is 457 mm instead of the 30.5. This is 40 point, instead of the 30.5 mm in the standard Proctor test. So there are several factors affecting the compaction. So we have the grain size distribution, the shape of the soil grains, the specific gravity of the soil solids, and the amount of and type of clay minerals present in the soil. So the next one is we have the effort of compaction. So the compaction energy per unit volume can be calculated using this equation. So we have the compaction energy per unit volume denoted by E. So this is equal to the number of blows per layer times the number of layers times the weight of the hammer times the height of the drop of the hammer all over the volume of the mold. So you can um, notice that the compaction energy per unit volume in the modified Proctor test is greater than the compaction energy per unit volume in the standard Proctor test. So comparing the two, they have the same um, number of blows, but the number of layers, the weight of the hammer, and the height of the drop of the hammer is much greater in the modified Proctor test. This is to mimic the field conditions. So that is the right term, to mimic the field conditions when the soils are compacted in the field using heavy equipments. So, and also for the volume of mold, the standard Proctor test and the modified Proctor test has the same volume of mold. So we have four compaction equipments. So first is the smooth wheel roller. So smooth wheel. So you will notice that the wheel of this roller is smooth. And then we have this is suitable for proof rolling subgrades and for finishing operation of fields with sandy and clayey soils. Take note, sandy and clayey soils. So, and also, obviously, it provides 100% coverage under the wheels with ground contact pressures as high as 310 to 380 kilonewton per square meter. So, of course, because it has this type of wheel, it will provide 100% coverage. But the smooth wheel roller, take note, is not suitable for producing high unit weights of compaction when used on thick layers. Next, we have the pneumatic rubber tired roller. So, unlike the smooth wheel, we have the spaces between the tires. So these are heavily loaded wagons with several rows of tires which are closely spaced. So we have 4 to 6 in a row. But in this model, we only have 4 tires. So 1, 2, 3, 4. And then the contact pressure under the tires can range up to 600 to 700 kilonewton per square meter. So this is larger than the 310 to 380 kilonewton per square meter provided by the smooth wheel roller. But because of the spaces between the tires, they can only produce 70 to 80% coverage. So they can also be used for sandy and clayey soil compaction. So, and then the compaction is achieved by a combination of pressure and kneading action. Next is we have the ship's foot roller. So, um, sorry the picture is a bit blurry, but in the ship's foot roller, the wheel is not smooth and it has smaller projections that that looks like the foot of a ship, and these are drums who with a large number of projections. So you can see that small ones. They look like the foot of a ship. That's why it's called the ship's foot roller. The number of projections whose area may range from 25 to 85 square centimeters. So also they are the most effective when compacting clayey soils. And the contact pressure under the projections can range from 1,380 to 6,900 kilonewton per square meters. So during the compaction in the field, the initial pass says compact the lower portion of a lift. Then the top and middle portions of the lift are compacted at a later stage. So next is the vibratory roller. So these are very efficient in compacting granular soils, and the vibration is produced by rotating in center waves. So basically, any so basically, the smooth wheel, the pneumatic rubber tire, or the ship's foot rollers can be attached to the vibratory roller to provide a vibratory effect to the soil. And lastly, we have the handheld vibrating plates. So these are used for effective compaction of granular soils over a limited area. And then the vibrating plates are also gang mounted on machines which can be used in less restricted areas. So we use this type of compaction equipment for small scale projects usually because the equipment rental for the for large equipment such as the pneumatic rubber tire roller or the smooth wheel roller or the ship's foot roller is large, and and then the another thing to consider is the space. So isipin nyo dapat kung kaya bang ipasok yung ganong kalaking equipment in the project. So for example, um, the your project is in a very remote area and you hindi nyo kayang dalahin. Wala kayong papadaanan ng malalaking equipment. So you can use the handheld vibrating plates in those cases. And similarly for the construction of small buildings or usually residential, um, these um, these handheld vibrating plates are used instead of the heavy type ones. Or rather the larger ones. Um, Now let's proceed to the properties and structure of compacted soils. But first, let us determine two terms. So when we say dry of optimum compaction, the amount of water added is less than the optimum moisture content. While on the other hand, when we say wet of optimum compaction, the amount of water added to the soil is greater than the optimum moisture content. So these two have different effects on the properties and structure of compacted soils. First is the permeability. So when soils are compacted, the voids are reduced, hence the permeability is also reduced. Next is the compressibility. So this varies according to the applied pressure. So for low pressure range, the compressibility is more for soils which are compacted to wet of optimum than soil compacted to dry of optimum. So on the other hand, for high pressure ranges, the compressibility is more for soils which are compacted to dry of optimum than soil compacted to wet of optimum. Next, we have the shear strength. So shear strength of soil compacted to dry of optimum is more than those which are compacted to wet of optimum at lower strains. Next, we have the soil structure. So, soils compacted of dry of optimum have flocculated structure due to the attraction between the solid particles because of low water content. So, when we say flocculated, does soil particles look like this one? They are not arranged properly. Soils compacted to wet of optimum have dispersed structure due to repulsive force between soil particles because of high water content. So this one is the dispersed soil structure. Another is the swelling of soil. So when the soil is compacted to dry of optimum, the soil is in need of water. And it will swell easily when contacted with water. Unlike when the water is compacted to wet of optimum, the soil particles are oriented in a dispersed manner and swelling will not occur. So, to avoid swelling, the soil should be compacted to wet of optimum. Next is the shrinkage. So, shrinkage is more for soil compacted to wet of optimum than dry of optimum. So in case of dry optimum compaction, soil particles are in random orientation and they are in stable condition. But in the case of wet of optimum, soil particles are in parallel orientation and they are unstable, which makes it easy for packing of particles causing shrinkage. Next is the stress-strain behavior of soil. So soil is compacted to dry side of optimum will take more stress for little strain. The stress strain curve of this type of soil is much steeper and elastic modulus is more. So brittle failure occurs in this case. Similarly, soils compacted to wet of optimum will produce more stress even for smaller stress. Hence, stress-strain curve in this case is much flatter and plastic type failure occurs at a larger strain. So this type of soils have low elastic modulus. And lastly, we have the pore water pressure. So when we say pore water pressure, this is the pressure induced to soils because of the water in the void spaces. And these topics, the stress strain behavior, I think will be discussed in the second part of our subject. I think there's still geotechnical engineering too. But the pore water pressure it will be discussed in the next chapter. So this is included in the vertical stresses for soils, I think. So since the pore water pressure is the um, pressure induced to the soil by the water in the void spaces of the soil, it will be high it will be high when the water content is high. So hence, the soils compacted to wet of optimum compaction will exhibit more pore water pressure than soil compacted to dry of optimum. So these are my references in this video. We have the Principles of Geotechnical Engineering by Braham Das, and the last topic, which is the properties and structure of um, compacted soils, is taken from this site, theconstructor.org. If you want, you can have further readings in the in the topics I have discussed earlier, and see you in the next video for the remaining topics, such as the specifications, the determination of field density of soils, as well as the California bearing ratio test, and for the example problems. So see you guys next week. And if you like, you can also subscribe to my channel and hit the notification bell so that you will be notified whenever I will be uploading new lessons. Bye!